In this video, we are going to solve an integrated question involving the equation of the tangent. The center of circle C is at 0, 6, whose radius is denoted by r. The straight line L, kx minus y plus 14 is equal to 0, is a tangent to C. Part A, express the equation of C in the standard form, in terms of r. This is very straightforward. It's the square root of x minus 0 plus the square root of y minus 6 equals the square root of r. So, it's x squared plus y minus 6 all squared equals r squared. Part B, we need to express r squared in terms of k. What we'll do is to make y the subject of the equation of L and put it into the equation of C, and then make use of the relation that L is a tangent to C to get the answer. Let's see how it works. Form a set of simultaneous equations with the equations of L and C. Make y the subject of the equation of L, which will be in terms of k. Substitute this into the equation of C. Carefully simplify it. We'll obtain a quadratic equation in x, whose coefficients contain the unknowns k and r. L is a tangent to C, so what? So, the discriminant delta of the quadratic equation we just set up is equal to 0. Now we've set up another equation in k and r. Rearrange it to make r squared the subject. We have r squared equals 64 over 1 plus k squared. Part C. It's given that L passes through the point 2, 12. In C1, we need to find the value of r. To do that, we put the given point into the equation of L to find k, and then use k to find r. Putting 2, 12 into the equation of L, k is equal to -1. Then, putting the value of k into the expression we found in part B, r squared is equal to 32. And r is equal to 4 times the square root of 2. Since r is a radius, it must be positive, so we'll reject the negative case. For C2, L cuts the x-axis and the y-axis at the points D and E respectively. And there is a point F such that C is inscribed in triangle DEF. Note that C is inscribed in triangle DEF means that C touches each side of triangle DEF at exactly 1 point. We need to determine whether triangle DEF is an obtuse triangle and explain it. To have a better idea of what C and triangle DEF look like, let's sketch it out. The value of k was found to be -1, so the equation of L is -x minus y plus 14 equals 0, which has a negative slope. D is on the x-axis, so its coordinates are 14, 0. E is on the y-axis, so its coordinates are 0, 14. Mark the approximate positions of D and E and sketch a graph of L. Then, mark the approximate position of the center of C at 0, 6. C is a circle that touches L, so it's something like this. Next, sketch a tangent to C that passes through E, and another that passes through D. The point where these two tangents meet shall be the point F. Now we've got triangle DEF. Judging from the sketch, angle DEF is likely the angle of concern. So let's see if we can find it to draw a conclusion to the question. Let G be the center of C, and A be the point of contact of L and C. Join GA. We know the y-intercept of L is 14, and the y-coordinate of the center of C is 6. So GE is equal to 8. And as a tangent property, GA, a radius of C, is perpendicular to its tangent L. So triangle AEG is a right-angled triangle. Sine of angle AEG is equal to GA over GE. GA is a radius, so it's equal to 4 times the square root of 2, and GE is 8. Therefore, angle AEG is equal to 45 degrees. Then, by the tangent properties, we have angle FEG is equal to angle AEG. So, angle DEF is twice that of angle AEG. That is 2 times 45 degrees, which equals 90 degrees. Therefore, we can conclude that triangle DEF is a right-angled triangle, but not an obtuse-angled triangle. There is an alternative way to find angle AEG. We consider the x-intercept and y-intercept of L, so that we can find the lengths of OD and OE, which are both 14. Then, considering the right-angled triangle ODE and the tangent ratio, we can also find angle DEO, or angle AEG, is equal to 45 degrees. That's it.